welcome to the Distinguished Lecture Series. I'm Karen Matthews of University Video Communications. Our program is designed to enrich graduate and upper division curriculum with academic presentations from top computer scientists in industry. Speakers and topics were nominated by computer science faculty of more than 50 universities. This presentation is sponsored by Apollo Computer. Dr. David Nelson, a leading figure in computer architecture, received his PhD in physics from the University of Maryland in 1970. He has managed research at Digital Equipment Corporation and directed research and development at Prime Computer. He is now Vice President and Chief Technical Officer at Apollo Computer. His talk today is Network Computing. It's our pleasure to introduce Dr. David Nelson. Dr. Nelson.
Thank you, Karen. Before I begin a detailed discussion about the technical aspects of network computing, I'd like to build a context, a way of thinking about architecture and the technology in general. And I have developed a number of axioms that I, on the one hand, think are very simple and easy to understand, but on the other hand, I think are relatively significant and provide some insight. The first such axiom is the idea or the observation that computers over the years have generally cost an equal amount in terms of weight. And I've observed that independent of time and largely independent of the size of the computer, that figure on the order of $200 to down to $100 a pound is not a bad estimate for how computers compare to each other. Another axiom is, again relating to weight, is the idea that weight is a very good determinant of use. In the sense that a department, for example, might use 500 pounds of computers, whereas an individual might use 50 pounds of computer. A personal portable computer might be as little as 10 pounds, for example. And when we view computer architecture this way, we can derive a system of tiers which really start with very large environments such as campus environments, and then a tier lower than that going to a building environment, and then further down is a department, an office, and then you get into the personal area, which is briefcase computers, laptop computers, and even wallet-sized computers. And one interesting thing about this is that over time the technology going across these multiple tiers has very accurately correlated weight to that environment. We've observed another axiom, which is that the technology rate through these various tiers is approximately 35% per year. When you compound that over a period of about 7 years, you observe about a factor of 10 improvement. And so if we were to show that changes across the tiers as a function of time, we would get some very qualitative differences in the machines at each tier. We have here a chart which shows the computer developments beginning in approximately 1960 and extrapolated out to about 1990. And vertically is the logarithm of the cost of the machine, or accordingly the weight of the machine. And so we find that the technology following an exponential curve at 35% a year is represented here by the series of straight lines, beginning at the upper left and then migrating slowly toward the bottom. We have found that concepts such as large virtual address spaces and large physical address spaces and many other concepts such as hierarchical file systems and other properties or characteristics of computers typically obey this downward trend beginning at the top and evolving toward the lower right. When we populate these with workstations, we see that there is a further refinement of workstation products in that workstation tier. The problem that this all generates is that as time goes on, the tiers become more and more populated with computers. So these days we don't find simple environments. We find environments that contain a variety of computer sizes, ranging with very large supercomputers at the top and building mainframes in the mid-range and department-sized computers lower down, and then finally workstations at the lower tier. And this, in part, has motivated the development of a network computing model, which is what I want to focus on primarily in this lecture. Network computing, in our judgment, should be viewed in a much broader context, which includes some predecessor architectures. Basically, we view each of these architectures as being generational. That is, one mode of computing lasted perhaps a decade each, and then it gave way to the subsequent mode. So while the 1960s was largely associated with batch and the 1970s was largely associated with time sharing, Apollo Computer and others developed the idea of distributed workstations as being the principal architecture for the 1970s. We are now developing a technique which we refer to as network computing, which positions the entire environment for the 1990s. One interesting way of viewing this transition is to observe the ratio of computers per user over a very long period of time. The number of users per computer back in the 60s was literally thousands or more, servicing a fairly wide community. The 1970s reduced that number down to approximately 100. The 1980s, with Apollo and others and personal computers, we reduced the ratio down to about 1 to 1. The interesting question here is whether that ratio or that trend in the ratio will continue or will it stop with 1 to 1. And in fact, we believe that it will continue, that the ratio will invert itself so that the number of computers will actually outnumber the number of users by a very significant margin. We could envision in the mid-90s of applications, single applications, doing single functions, taking advantage of literally hundreds of computers working collectively, partly in parallel, partly sequentially, but all to serve some greater goal or objective of the user. This diagram more or less shows some of the physical configurations of computer systems as they have evolved from the 60s and on. And in the lower right, we show a typical configuration of a network computing environment. Now, I would stress in this diagram that we are not thinking of simply connecting together a large number of computers, but rather we are developing a technique whereby a single application can dynamically run across an environment that's shown there, taking advantage of, say, a Cray, or taking advantage of an IBM mainframe, taking advantage of the graphics on a workstation in one integrated solution. There are many dimensions to network computing. It includes certainly the user view. And in this area, we regard the X Windows standard developed at MIT as being very fundamental to the technique of exporting the user view across a network. Network computing services is in the second area, and here the yellow indicates systems which have been developed and are in place, and white indicates areas that are yet to be fully developed or explored. Further on, distributed data access, and further on is network administration issues. I'm going to narrow in on this broad view by focusing on the network computing architecture and spend the rest of the time pretty much on this area of network computing services. We look at the whole problem of network computing as being constructed, or I should say supported by two pillars, if you will. One pillar being that which is associated with network data, and the other pillar being that which is associated with network computing. These two pillars, to some extent, represent the history of networking, and the other pillar represents the future of networking. If you reflect on it, I think you'd agree that most of the networks over the past 25 or 30 years have been pretty much exclusively designed around the idea of transferring or accessing data. If you consider X25, the ISO model, and many other networking schemes developed by various manufacturers, they have been principally developed for the purpose of transferring files or accessing files in place. The idea of accessing computation on other machines has been rather late coming. rudimentary at best, and generally thought of as an afterthought, taking the principal role as being the axis of data. That's been the history. The future is to re-examine networking and see if we can't build a far more comprehensive model to truly do distributed processing, using all of the features that have been previously implemented regarding data access, but advancing these principles to solve the complementary problem of network computing. Frequently, the question of why now is raised. The idea of distributed computing is not a new one. Its history goes back at least 15 years, if not further. This has been a rather well-explored topic. We have had numerous proposals and implementations and research studies, and languages have evolved and architectures have been developed, all for the purpose of distributing an application. But I think there are two trends that are occurring, or two significant happenings which cause a commercial supplier like Apollo to take a good hard look at this technology. The first, I'm going to comment on in a few moments, is basically the emergence of a large number of server hardware, which is being developed and now being marketed on the on networks in the industry. The second is certain advances in the area of software engineering, and I've prepared a very brief sequence over time of what I thought some significant happenings were in the area of software development. While I won't go through these in detail, there is an interesting trend that occurs when one looks down the chart from 1960 on. The 1960s generally was the first decade to embrace high-level languages in any meaningful way, and so we saw languages such as Fortran and COBOL, which to these standards are largely regarded as unstructured languages, and so people didn't have any structured approach to either code or to data objects. The 1970s emerged with the concept of structured programming. Structured programming then led to the development or the modernization of Fortran and the Fortran 77 standard, and ultimately to the broader acceptance of C and Pascal, and these days practically all languages embody some form of structure in the programming. They did not by and large address data in a complete way. The 1980s are doing to data what the 1970s did for code. That is, it is through the techniques which are referred to as object-oriented design. We are now adding a high degree of structure to data by essentially encapsulating it into objects, encapsulating data and procedures into objects, allowing the internal state of these objects to be varied and hidden from the rest of the world, placing a high degree of emphasis on the external interface of the object, and attempting to describe applications more as relationships or interactions of objects. The significance here with regard to network computing is that to the extent we can, in fact, think of applications as collections of objects, we have, in essence, decomposed a large, linear, complicated address space into a number of independent, smaller address spaces. And since we've then decomposed the virtual address space, we can in turn then think of decomposing the physical address space and in fact assigning each of those address spaces to a unique physical machine. So to some extent, the network computing architecture can be thought of as an application which is comprised of a set of distributed network-based objects. Now, a good deal of the formalism and the theory, I should say, behind network computing is described in terms of object-oriented design. Having said that, however, it's important to realize that this requirement does not extend its way into the application. The network computing system that I'll be describing here is very appropriate for non-object-oriented languages such as C and Fortran and Pascal and others. But much of the theoretical description and the architectural description of network computing is in fact described in terms of object-oriented design and is most appropriately thought of in terms of object-oriented designs. The other trend I want to get back to is one really comprised of two trends, one in the area of applications and the other in the area of hardware development. And my assertion here is that these two trends are really diverging and proceeding in opposite direction, requiring, therefore, something like network computing to bring them back together. Simply stated, the trend in the area of applications is toward integration of multiple disciplines of computation. And here we refer to a discipline as being, say, computation, which is highly numerical, or graphics, which is obviously graphics, simulation, which is frequently logical in its nature, data management, AI, and many others, all of which here we think of as being generic forms of computation. Now, years ago, we would find applications that would exclusively involve one discipline. For example, we might find an application that simply did computation, or another application, modeling or drafting, which simply did graphics. These days, however, application developers are tending to integrate multiple disciplines together into a single application. Clearly, in the area of workstations, we integrate computation and graphics in a very integrated way. And in the area of electronic design, we include things like simulation. And in the area of mechanical solids modeling, we very much integrate data management, not to exclude the others, such as AI and testing and so on. So the tendency here is very clear, and that is one of integrating multiple pieces of this puzzle together into a single application. What is the problem with this? The problem, simply stated, is that hardware does not generally map well onto this puzzle. Hardware, in fact, is going more or less in the opposite direction, as shown here. Hardware, while applications are integrating, one could say that hardware is somewhat disintegrating. That is, they're specializing in their design. So rather than finding a processor or a machine that can equally well run all of the various generic types of computation, we find just the opposite, that products are being developed to run one type of computation very well and neglecting altogether the other types. And basically developing these components as servers to be integrated at the network level. The reason for specialization in the area of hardware is complicated, but it's very compelling to look at the results. This chart compares the price-performance ratio of special-purpose machines to general-purpose machines as a function of a typical figure of merit of computation. So, for example, if the application requires integer MIPS, we can go to a special-purpose computer and buy it at roughly a 6-to-1 advantage over a general-purpose computer. If our interest is in megaflops, we can have a 10-to-1 advantage. If our application is AI-oriented and therefore logical inferences per second, we can find a 4 to 5-to-1 advantage simply by going to a special-purpose computer rather than a general-purpose computer. Similarly, for transactions per second, we have a 12-to-1 advantage, and for events per second for simulators, MTBF for fault-tolerant systems, vectors per second for graphics systems. All of these give a significant advantage when the customer essentially buys a special-purpose computer rather than a general-purpose computer. The problem is, of course, that applications don't map well onto this hardware. But what we want, therefore, is a runtime environment that essentially allows for the application shown on the right, comprised of multiple pieces, multiple components, to be executing transparently on the configuration shown on the left. Assigning dynamically, perhaps, the computational part of the application to a compute server, the graphics part of an application to a workstation, the data management part of the application to a database server, and so on, so that here we are able to have the better of both worlds. We're able to perceive and develop the application as a single entity on the one hand, and on the other hand have its execution occur on the machine which is best designed for that type of application. The challenges are manifold. I've introduced a few of them here. Foremost, perhaps, is to leverage the rather significant investment that the industry has made in the area of software engineering. And so, to this goal, we have insisted that there be really no new software engineering concepts introduced in the network computing system. We want the software engineer to think of the application as being singular, integrated together, and we want the concept of assignment to be dynamic. We want to have the perception on the part of the user to be one where the user is not necessarily aware of where computation is taking place, and so on. So on the one hand, we want to have the logical advantages of a single application and do so in a manner which does not introduce any new programming concepts. The second challenge is to take advantage of the dynamic nature of networks. And here we use terms such as accommodate and exploit to describe our objectives here. Applications should not be dependent on any particular network configuration, but rather they should accommodate a variety of configurations and in fact accommodate them in real time as the configuration of the network changes. Machines, after all, can go up and they can come down, networks can break, and so on. So we like to think of the application rather like an expanding gas, where the gas is rather contained by the pressure exerted on it through a vessel or whatever. As the pressure is released and the vessel more or less expands, the gas expands to fill it. And conversely, as the environment exerts pressure on the gas contracts. And the metaphor here is applied to networks in the sense that as networks break, the application should contract and accommodate whatever environment that it sees. And conversely, when the network is repaired, the application should suddenly somehow expand to take advantage of that repair. The network computing system that I will describe in a little more detail here exists currently as three major components. These components exist on not only Apollo computers, but they exist on many other, or most other competitive machines. They've been ported to and continue to be ported to a wide variety of workstations, a wide variety of server processors, and so on. The three components here include a locating broker, a RPC architecture, and an NIDL or NIDL compiler. The locating broker is a database in the system which helps facilitate what we refer to as deferred binding or dynamic linking. Now, binding is a process, as we all know, of one of linking together or binding together various software modules, typically subroutines or procedures. Binding is usually static. That is to say that developers bind or they compile a series of modules and then they bind them together into a static executable unit. Some systems have employed dynamic linking or deferred binding in the context of an operating system to facilitate linking to libraries and so on. But by and large, applications have gone through static binding techniques. We have implemented a technique of deferred binding largely for the purpose of deferring the binding problem until execution time, where we can take better advantage of the information about the state of the network. So rather than bind two modules together, one on a workstation, one on a mainframe, ahead of time, we would rather defer and make that decision at execution time to take advantage of the fact that maybe the mainframe is down or too busy or whatever other dimensions of the problem might be imposed on it. So by implementing dynamic binding or deferred linking, we can essentially create a much more dynamic environment and assign the various procedures or modules of the application to the appropriate part of the network at execution time. I have mentioned the idea of procedures. Procedures are the basic building blocks of applications. Procedures are generally implemented, referenced from one module to another through a procedure call, and we have implemented remote procedure call, largely as a mechanism to transfer control from one computer to another. So the way in which we dynamically assign the program from one computer to another is at the procedure call level, and we do it through what's called a remote procedure call architecture. RPCs are not new. They have been fairly well explored over the last 10 to 15 years. They've been implemented in numerous systems, including ours and others. But the unique thing about the NCS RPC is the way in which it interacts with the NIDL compiler, which I will describe in a few moments, so as to provide application-level transparency. Application-level transparency is required here because we don't want the software developer or the application developer to be necessarily aware of how the application is in fact going to decompose across the network. So we are able, rather than to assign specific procedure names to do RPC, we are able to allow application-oriented procedures such as invert a matrix or whatever to be dynamically assigned to various machines in a way that is transparent to the rest of the application. It's important to understand how these three components play together in the context of a real application. In order to consider a real application, let's consider the dimensions of a typical application. For example, it may be comprised of literally dozens or hundreds or more procedures. These procedures can in turn be nested to some arbitrary level of depth. Procedures can call procedures, which in turn can call other procedures, and this nesting of procedure calls can be quite deep. So in a network computing environment, when we want to dynamically switch from one computer to another at the event of a procedure call, it's pretty clear that we could develop a very, very complex environment, because one procedure call could call another computer, which in turn could call another computer, which could call my computer back again, and this could wind itself into a very complicated state. Now, in order to understand all of that, what I'd like to do is to describe a very simple application, in fact, the most trivial application that involves a procedure at all. And that's shown on this slide, which at the top center has one application comprised of a main body program and one procedure. So the idea here is that the application developer think of and design the application as being very simply a main program and one procedure. It is desirable, however, to run, for example, the main program on the Apollo system on the left and the subroutine or the procedure on the VAX computer on the right. We want to do that in a way that preserves totally, if possible, the procedure call interface. The procedure call interface can include parameter passing and a variety of other things which can complicate the environment. We want further to perhaps run the procedure not on a specific VAX, but we may want to run it on, say, one of a family of VAXes. Perhaps the environment has 2 or 4 VAXes. We might also want to run the procedure on a mainframe computer, which is not shown on the diagram. So the policy may be something like run the procedure on the mainframe if it is available, and if it isn't available, then contract and run it on one of the VAXes, and if they aren't available, whatever that might mean, then contract and run the subroutine on the Apollo. But from the user's point of view and from the software developer's point of view, that assignment is not important. The point here is that the application from both the developer's and the user's point of view is perceived as a single entity, and the assignment of the procedure is done dynamically by the system in conjunction with the locating broker. The assignment of procedures to other machines is obviously not trivial. We have a number of problems to overcome here, not the least of which is the dealing of parameters, which in part can be called by value, in part can be called by reference. There are other issues such as dealing with pointer variables and variably dimensioned arrays and things like that, all of which have to be dealt with by the network computing runtime environment. Furthermore, we have differences in machine architecture. Clearly, these two machines have different representations for floating point, and that turns out to be a relatively easy thing to deal with. More complicated, however, is the fact that the two machines order bytes differently to form integers. And so while on the Apollo we form it one way, the VAX forms it another way. And so we need much lower level information than is typically provided by languages or by file systems and things like that to essentially solve this byte ordering problem. Obviously, the runtime environment has to deal with the dynamics and uncertain nature of networks. The fact that machines fail while applications are running, and so the runtime environment has to monitor the machines to which they have assigned work, and so on. There's a high degree of complexity associated with the runtime environment. So consequently, we introduce this concept of a stub. A stub means that something remains after you break it off. And so in moving the application to the machine on the right, or the subroutine to the machine on the right, there remains a stub on the machine on the left to totally mimic the missing part on the left. Similarly, on the machine on the right, we introduce a stub to totally mimic the missing main program on the machine on the left. The stubs then cooperate in dealing with all of the problems that I have mentioned in a way that minimizes, if not eliminates, all of the additional complexity on the part of the application. The problem then becomes one of who generates the stubs, how do we generate them, who manages them, who maintains them, and who guarantees their integrity, and so on. The stubs are generated by another part of the NCS architecture, which is called the NIDL compiler. NIDL refers to Network Interface Definition Language. The interface definition language is shown at the very top of this slide in blue, and basically contains a description, an interface definition of where the application is to be partitioned. It contains the names of the various procedures, contains a list of all the variables that are passed. Most importantly, it contains type information associated with each of these variables so that we can subsequently solve this problem of byte ordering and different formats for data types. The NIDL compiler reads the interface definition and essentially automatically generates the stubs. The stubs are then compiled on the various target machines, in this case an Apollo on the left and a VAX on the right, and in addition it can be compiled on various other machines such as a mainframe. The stubs are then compiled and bound together with the various component of the application to form a server process. And so what we have done here is develop a dualistic view of the world. One view is one of the application, which still appears to be singular. That is, we still think of the various application components as being a collection, or I should say parts, of a single program. The other view is that after we run the interface definition through the NIDL compiler and bind it together with the application component, thereby producing a server, we at that point have a client-server model of the world, where one server processor or one server process is referencing other server processes and so on. It's important to have this latter point of view because only in this way can we build a runtime environment and operate it on top of conventional operating systems such as Unix and VMS and others. Because most of these operating systems do embody some form of a server view of the world, clients and servers and the like. I'd like to mention a few other aspects of the network computing system. The first here refers to the locating broker, which I have briefly already described. The functions of the locating broker are to track network resources, for sure, and to essentially deal with the dynamics of the network. The locating broker is best understood in terms of the client-server model. The purpose of the locating broker is to really prevent clients and servers from requiring complete knowledge about the network. Rather than having everyone know everything about everything, we put all of the knowledge in one place, basically in the broker. It behaves then as an object-oriented database and is referenced by clients and servers to obtain information in much the same way that a broker serves in the transaction of a real estate sale. Real estate is listed and sold in a broker largely to provide both buyer and seller with wider knowledge than what they would otherwise have. The locating broker is made aware of network services through what is called a register function or a registration function. Basically, as servers are assigned to machines and they become operational, the first thing they do is to register their availability with a broker. Subsequently, when the application is executing, the locating broker is referenced to find out what the complete set of information is relative to that particular service and make some policy decision as to which machine to be used. The policy decision is complicated but could include the level of loading on the various machines, what machines are available, what networks are available, what sort of special hardware is available on the machines, and many other issues as well. Several other aspects of the computer system is to allow for the execution on a variety of transports and to work in a multi-vendor environment, which is clearly required in order to realize the objectives that we stated earlier. We have developed the system so that it is layered in on top of a number of different types of protocols. Basically, the runtime environment employs what is referred to as a connectionless, unreliable datagram service, and such a service is generally found in a variety of protocol suites, including ISO and including TCP/IP and a variety of others. In this way, we're able to take advantage of not only the software that has been developed, but also hardware architectures that take advantage of those protocols. Further function is to be transportable to another number of operating systems. The specification of the network computing system is in the public domain. Source code is licensable at a very low cost, and furthermore, there is no binary license fee on the part of users or application suppliers or other vendors to employ this system. So we have created a fairly complete scenario, and we expect it to be readily used on various Unix systems as well as VMS, and including, in fact, IBM PCs running MS-DOS. I'd like to present an example which I believe illustrates many of the advantages of network computing. In this example, it is one of mechanical simulation used by automotive industries, aerospace industries, farm equipment manufacturers, and so on. The problem is, how do you simulate a very complex mechanical device that on the one hand requires mainframe levels of computation to simulate, and on the other hand would be desirable to be able to view the simulation as it is occurring. Typically this is not done, but rather an engineer employs a series of preprocessors and simulators and post-processors and generators of animation sequences and so on. With network computing, we replace all of those various applications with a single application whose graphics part runs on the workstation and computation part runs on a mainframe. This really allows the design engineer to do two things they've never really done before. First of all, they can, for the first time, visualize the results of mainframe computation. As the mainframe is computing, it is very rapidly making procedure calls to the workstation. The workstation is then in real time rendering the effects of that simulation so that what the user is seeing at the workstation is the visual results in real time of the simulation being performed on the mainframe. The second thing the design engineer can do with this application is to begin to interact with the problem of simulation. We could envision velocity controls, for example, that would allow the simulation to even run in reverse. We can envision the dynamic adjustment of parameters, in this case perhaps the suspension system of an automobile, to tune it, if you will, in the simulation without having to iterate over various design parameters. Furthermore, with a multi-windowing environment, we can create multiple windows, each of which has an aperture into the mechanical model. We can zoom in on problem areas and reverse the simulation, run it in slow motion, and so on. So the bottom line is that with network computing, we can bring the resources of the mainframe down to the desk of the design engineer with no real artificial boundaries imposed by the network. Bring those computational cycles to the desktop and allow them to be applied to what would otherwise appear to be a graphics-oriented problem. A further development of network computing is the ability to run concurrency in the network computing. This essentially involves the ability to run a large number of computers in parallel, as shown here. dynamically assigning them, perhaps in fairly large numbers. As a final thought on network computing, we'd like to consider many of the operating system implications. Once one distributes the upper layer, the application layer, one develops a lot of problems having to do with security, licensing, accounting, scheduling, and the user environment. Basically, what is going on is the industry is developing a comprehensive model to deal with these operating system functions, re-implementing them, rethinking them, re-engineering them. So many of the features found in traditional operating systems will in the future be placed at the network level in terms of vendor-independent, operating system-independent servers, and thereby reducing the complexity of the workstation dramatically. We in fact intend that network computing could be the first environment that would transparently operate across multiple operating systems manufactured by multiple vendors and applied in a fully distributed environment. Licensing server is one example of a server-based operating system component shown here that will essentially give application suppliers much more flexibility in how they license server. We are beginning to develop equivalent models for dealing with authentication, accounting, security, the user point of view, and so on. So what I have described to you is a network computing architecture which we believe represents a new generation of computers, has the advantage of taking advantage of many different types of computation, all applied to what would be viewed as a single problem or a single application by both the application developer and the end user.
I'm Judith Lemon from University Video Communications. Our first 4 faculty questions are from the University of California at Berkeley. Dave, number 1, what do you see as the role of multiprocessors in workstations?
Well, multiprocessors already occur in workstations. We find, for example, on the one hand, there may be a main CPU doing general applications, and on the other hand, a graphics CPU doing graphics. So what we are attempting to do is to generalize that dichotomy that already exists, make these general-purpose computers in general, but making the general-purpose computer more robust in its ability to perform not only computation but graphics. So at the high end, we see a very strong role, an important role, in multiprocessing, and moreover, we see these processors being generally applied not only to applications but also for high-end graphics processing.
Question number 2 for you is, do you think RISC ideas in workstations are a fad?
Well, I'm not sure I would characterize them as a fad. Clearly, there's a lot of merchandising and so on going on associated with RISC. We think there are a lot of valuable ideas associated with RISC techniques, but we don't think that they ought to be exclusively applied to the design of a computer. We think RISC is one component in many different components, all of which can be applied to the design of high-performance computing. Basically, RISC is the result of there no longer being importance placed on a machine language architecture any longer, allowing high-level language compilers to have direct access to the computer.
Okay. What is the role of mainframe, and supercomputers in workstation environments?
Well, I think the role now we are becoming more and more aware through network computing and other techniques that the role is one of integrating together. The problem is, and will continue to be, how do we get the MIPS that the mainframes and the supercomputers supply and the databases that these machines supply down to the level of the individual user? Network computing can be applied to that problem, and we believe solve it very nicely.
Why does Apollo think that 4 MIPS is enough in 1987, but needs significantly more MIPS in 1988? What demanded this big change?
Well, fundamentally, the reason for the disproportionate jump in performance rates is basically driven by what technology offers us. If we take RISC technology and we take very large-scale integration of circuits and apply them to chips, and and do some organizational things in the design of the computers along the lines that I've just mentioned, we believe that technology will allow us at the high end to actually deliver those kinds of performance levels. The applications that we envision for this are numerous. Seismic analysis, finite element modeling, in terms of graphics would include three-dimensional solids modeling. There are numerous applications for high-end computing, and users continue to be demanding more and more computation. So there's clearly a market need, and the basic thing that's driving us is the availability of the technology that we see forthcoming.
Mm-hmm. What do you see as the next generation of computers beyond workstations?
Well, beyond workstations, I think that's a very broad and long-ranging question, I suppose. But one of the things that I, as a user, have been interested in for some time is the application of portable computers to many engineering problems. If we think of a workstation as being confined to an office and confined to a specific network, basically what we want to do is relieve those constraints, reduce the confinement, allow the user to carry the system around with them, allow the system to automatically know where it's been, know where it's going. If it's at home, it should know it's at home. When it's in the office, it should know it's in the office. It should be able, through ISDN techniques perhaps, be able to connect in a very broad way all over the globe and in a very dynamic way, depending on the nature of the problem. So I think we will see in several years the forthcoming of very, very capable portable systems, which are really well beyond what we see today in portable computers, but will include these characteristics of being able to dynamically adapt itself to an environment.
I like that idea. And finally, now how do you manage to keep up with the rapid change in computer development? What kind of a framework would you recommend to students for doing this?
Well, I personally have relied on the idea of models and trends over long periods of time, and to look at deviations off of that model. That is, rather than look at rates of change in terms of their absolute value, look at the deviation in rates of change over a fairly long period of time. I think it's as valuable to look at the things that don't change as it is to look at the things that do change. For example, the cost per pound of a system is one of the constants that I alluded to earlier. The 35% per year as a function of time is another constant that seems to have prevailed over several decades, although in the workstation area the rate of change is significantly higher than that. So basically, I like the idea of developing a very simple model that is uniform over a long period of time, and then looking at the deviations relative to that model.
Well, thank you very much.
Thank you. I enjoyed being here.
And thank you for joining us today. We invite your comments and questions, and we hope you will nominate future speakers and topics. For these purposes, we have provided, under the label of your video cassette, feedback postcards. Thank you again.